Welcome back, biology students. Today we are going to be practicing the scientific method vocabulary and also starting to look at some of the factors that affect how a population of organisms might grow and change and increase and decrease in size due to different factors. So this is called the Avril Gulf tuna population simulation. We're going to go through this tutorial first so you have an idea of how this works. It says, welcome to Avril Gulf. In this simulation, you'll investigate how various factors influence the sustainability of the Avril Gulf tuna population. In the top left corner of the screen, you will see your population of fish. In the top right corner, you'll see a graph that's showing how the number of fish in the population on the y-axis changes over a 20-year period on the x-axis. In the bottom right, you see variables that can be changed for each scenario. You can reset or pause the simulation at any time. There are 4 stages to the simulation. As the simulation runs, you can alter the values of the variables. All you need to do is move a slider to change a variable's value. It may be a number or a simple on or off. In each stage, your goal is to determine at what value the variables need to be set for the population to reach and stay at a sustainable carrying capacity. That means you're trying to determine the best conditions for your fish population to remain a good size and stay that size steadily over time. After 20 virtual years, if you've not completed the stage successfully, you can try again. At the end of each stage, a print button will appear. We're not going to print anything. And there will be more specific instructions as we go through. Good luck. So we're going to start here with the first scenario. In this stage, you'll examine how birth rate, death rate, and migration rate affect the sustainability of the Avril Gulf tuna population. So you can see in the lower right-hand corner, there are 3 sliders that can be adjusted here: reproduction, migration, and death. Those are the 3 variables that can be changed for this particular stage. So for this first scenario, I'm just going to leave them all right where they are. So you'll notice they all start right in the middle. And we're going to play this and watch how this plays out. So you can see the pictures of your fish appearing on the left. And on the right, you can see the graph of how our population is growing and changing over the years. We'll let this run all the way to year 20. And now we're going to start making some changes. So this is the graph of how our population changed through this first trial. I'm going to click this button to show history. So this first line will stay here, and you'll be able to see how this changes each time. So this first one, I'm just going to write on here so that you can see. This first one was our population with every slider set in the middle. So what we're going to do next is we are going to change this reproduction value. We're going to slide this all the way down to low. So now we have a low level of reproduction. We left migration and death the same. And we are going to play through that scenario. So you'll notice it left our original line on the graph, and now it's creating a new line as we run through our 20 years of data with low reproduction rates in our fish. So that was the line with low reproduction. Now we're going to do one more trial here. We're going to reset our values again. This time I'm going to slide reproduction all the way up to high, and we'll see what happens this time. So take a minute and study the 3 lines on our graph. We had low reproduction rate, medium reproduction rate, and a high reproduction rate. and answer the questions that you see on the right. Now we're going to move on to stage 2. In this stage, we're going to examine how predators, the amount of food, and incidence of disease and pollution affect the Avril Gulf tuna population. So we're looking at a few different factors in this one. So as we start stage 2, you can see the sliders down here in the bottom right have changed. Now we have one that says how many predators, from none to many, how much food is available, from little food to abundant food, and disease and pollution. And so this time, I'm not going to touch any of those buttons. I'm not going to move anything. I'm just going to run it through and allow it to go through and collect its 20 years of data. And so this time you can see occasionally something like a disease happens, and you can see how that affects our population graph. Now with this scenario, we're actually not going to move any of the variables at all. We're just going to play it again and see if we get the same results. We had disease happen again. This time the disease lasted a second year and a third year. And we're going to run this one more time just to see what happens this time. Again, we get some disease for a year or two. And then we have another outbreak of disease amongst our fish. So again, take a look at those 3 graphs, all on the same graph there. Take a look at those 3 lines and make some observations and think about what this means for doing experiments with real-life organisms and kind of some of the challenges that go along with that. Now we're going to move on to stage 3. It says in this stage, we'll examine how fishing intensity and length of fishing season affect the sustainability of the Avril Gulf tuna population. So you'll notice a couple changes this time. At the bottom, we have 4 sliders that represent the amount of fishing from no fishing at all to heavy fishing that happened in the summer, the fall, the winter, and the spring. You'll also notice the x-axis of our graph has changed. We're not quite going through 20 years anymore, but it's showing us how the population changes from spring to summer to fall to winter each year. So we're getting a little more detail in terms of the seasons. So first of all, we are going to start with no fishing whatsoever. We're going to play through this simulation once and just watch how this goes without any fishing at all. You can see the different dots represent the different colors of the year. So that's spring, summer, fall, and winter. And they match the colors of the sliders on the bottom. This time we're just going to run this one more time and we're going to move all our sliders over to heavy. We're going to allow year-round tuna fishing in every season. And we'll play through that and watch what happens this time. Once again, take a look at this graph as you answer the couple questions over on the right. And now we're going to move on to stage 4. In this stage, we are going to be able to control all the different variables from those first 3. So we'll be able to manipulate all of them to determine their collective effect on the sustainability of the Avril Gulf tuna population. So now if you look in the lower right-hand corner, you can see that we can control the reproduction rate, the migration rate, so that's the number of new fish moving into this area, the death rate, the number of predators, the food. Disease and pollution will continue to just kind of pop up randomly. We can't really choose that, it just happens. And we can control the rate of fishing in all the 4 different seasons. So we're going to play with this one a little bit. And just for fun, we're going to think of it in terms of, instead of tuna in the ocean, let's think a little more like a Minnesota fish population, because lots of people like to go fishing here in Minnesota. So we're going to leave the reproduction rate kind of at average. But since most of the populations of fish here in Minnesota are lake populations, not a lot of fish migrate into a lake, right? So we're going to turn that down to low. We'll keep the death rate pretty much average, leave the predators and food as normal. Quite a few people like to go fishing in the summer, so we'll move our summer fishing to pretty heavy. And we also have some people that do some ice fishing around here, so we'll put kind of some light to moderate winter fishing in there. I think this probably is as close as we can get to kind of a fish population in a lake in Minnesota. So let's play that out and see what kind of graph we get here. Now, just for fun, we're going to play around with this a little bit and see how our fish population changes if we just mess around with some of these variables. So this time, let's say we have a really healthy fish population. So they have a really high reproduction. Oh, I have to reset this first. So we had low migration, heavy summer fishing, medium kind of winter fishing. Now let's say our fish are super healthy. So we have a high reproduction rate, lots of new baby fish, and a really low death rate. Some of them still die, but it's pretty low. So with super healthy fish, let's see what kind of difference that makes. Remember, the different dots on the graphs represent the different seasons of the year. Oh, there we had some disease in our population that year. All right. So we're going to run a couple more on here just for fun. We'll still say we have no migration, lots of summer fishing, some winter fishing, and we'll keep that really healthy population with high reproduction and low death. This time, let's put them in kind of a perfect, ideal environment. Let's say there's no predators and abundant food. Let's see how that does. So you can see our first 2 lines are still on that graph, so you can kind of compare each time we change these variables. You can compare how that's affecting our population of fish. Oh, disease for a couple years that time, 3 years in a row. 4 years, that's quite a fish disease. Okay. So we're going to run 1 or 2 more here. Let's see, I'm putting everything back. We had no predators. We had a lot of food, heavy summer fishing and some winter fishing. But now let's say sometimes in Minnesota when we really want to go fishing, we stock the lakes, right? We add extra fish into the lake so that we can go and fish for them. So that's kind of like migration, like adding new fish. So this time let's move our migration high and say we're heavily stocking this lake so that we've got plenty of fish to catch. So with healthy fish, we're stocking the lake really good. We have no predators, lots of food. Let's see how this one plays out. Still get some disease. There's nothing much we can do about that. And this time we got some pollution as well. So we're going to run one final trial on here. This time, we're going to try and make everything as good for the fish as we possibly can. So we'll say high reproduction, lots of migration, so lots of new fish coming in, low death, no predators, abundant food. But this time, we'll say no fishing is allowed whatsoever. So this is probably kind of the best case scenario for our fish population, right? So let's see how this one plays out. All right, we still got some disease there again. And some pollution. Oh my goodness. It must have been a major pollution event right there. Look at that. We'll run this one just like that one final time and just see how that works. So put all of our variables back to kind of ideal conditions. And no fishing at all. Last time through. So we still had some pollution happen in the middle. This time it looks like our population recovered. Oh, until the end. So take some time to think about this graph. We have all our different trials on there from the very beginning all the way through. As we continue through this unit, we're going to talk a little bit more about all the different variables that can affect how populations grow and change in size as they interact with their ecosystem. So answer the last few questions as you continue, and we're going to come back to this simulation and the ideas in here and talk about this throughout the next several days of class. So remember what you saw in the simulation and remember the types of things that you talked about in those questions.